Here in this video, we're going to take a look at an example where we're going to actually build a confidence interval from start to finish, and we're going to use all the tools that we've talked about up until this point. So here in New York City in October 23rd, 2014, a doctor who had recently been treating Ebola patients in Guinea went to the hospital with a slight fever and was subsequently diagnosed with Ebola. A poll consisting of a sample of 1,042 New York adults showed that 82% supported a mandatory 21-day quarantine for anyone who has come into contact with an Ebola patient. We would like to construct a 95% confidence interval for the proportion of New York adults who support a quarantine for anyone that has come into contact with an Ebola patient. So I'm going to work through this problem. I'm going to try and build myself a confidence interval. But before I do that, the thing about confidence intervals is that confidence intervals rely on the central limit theorem for proportions. In order for me to build a confidence interval, I need to check the conditions of that central limit theorem before I can continue on. So those two conditions, if we recall, were independence. Now, independence. That is a very difficult thing for me to verify. We've said before that we're going to use random sampling as sort of a proxy, as sort of a stand-in for that. Here in this case, we've got a poll consisting of a sample of 1,042. I'm going to assume that this is random sampling. This is generally not something that I'm going to try and trick you on and say, haha, I didn't have independent sampling. In this case, we can go ahead and assume that it's independent sampling. The one that I'm more worried about, the one that I do want to make sure that I check every single time, is called the success-failure condition. Success-failure condition. So this success-failure condition said n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Now, in this case, I don't actually have p. P is the population proportion right here. And that's actually what we're trying to estimate in this problem. We want to build this confidence interval for the proportion of New York adults who support this quarantine period. I don't know what P is, and this is the case most of the time. So in these cases, if I don't know what P is, we are going to use P hat as a stand-in for P. So we're going to substitute P hat for P, and basically all of our formulas that we might require for central limit theorem and things like that. So we're going to use n times p hat. Now, I need to know what n is and what p hat is before I can begin to answer this question. So let's take a look back up here at the top here. So n is our sample size. We said that we've got a poll consisting of a sample of 1,042 New York adults. So in this problem, we know that n is equal to 1,042. And I also want to know what is p hat. That's going to be really important for us. So p hat is a percentage or a proportion. In this case, we showed that 82% supported this quarantine. So 82% of my 1,042. So p hat is 0.82. So using these two things, I can go ahead and use them to find or calculate my success-failure condition, make sure that I verify those. So let's do that very quickly here. N we said was 1,042 times p hat is 0.82. Let me grab my calculator. So I have 1,042 times 0.82, and that gives me 854.44, running out of room. That's greater than or equal to 10, so that works. And then n times 1 minus p hat, I'm going to do that down here. 1,042 times 1 minus 0.82. So again, I'm going to grab my calculator really quickly. 1,042 times 1 minus 0.82 gives me 187.56, which is greater than or equal to 10. We have met the success-failure condition for our central limit theorem. So that's good news. That allows me to kind of continue on with this problem. Some problems in the homework or on quizzes and tests, they might just tell you, hey, you may assume that the necessary conditions are met. And if it says that, then I don't need to check these. It just says, hey, you can assume that the conditions are met. That's just a step that you can skip in those problems. So we are going to need to know what is n, and we are going to need to know what is p hat. So let's bring those down here. If I'm going to build and actually I should also make a note of what my confidence level is. We set a 95% confidence interval. So our confidence level is 95%. We're going to need that number eventually. So if I'm going to go ahead and build a confidence interval, the very first thing that I need to do is I need to find my standard error. So the standard error from our central limit theorem section said square root of p times 1 minus p divided by n. But I just said I don't know what p is. We don't have that value. So instead, we're going to go ahead and use p hat instead for those calculations. So my standard error is square root of p hat. We said 0.82 times 1 minus 0.82 divided by n divided by 1042. Be very careful with this calculation. It's a little bit more complex than some of the other ones that we've seen. If you're going to try to do this all in one step, make sure that you are careful with your graphing calculator. And if you have any issues with your graphing calculator, please let me know. I'm happy to help walk through the process. But I'm going to do that over here. I like to usually break it up into a couple of different steps. But the number that we end up with should be relatively small. So I ended up with 0.0119. I like to round my standard error to 4 decimal places right here, just because the numbers that we're going to be working with are pretty small. They tend to be very, very small decimals. So there's my standard error. Very cool. Once I have my standard error, I'm going to use that number to help me find my margin of error. My margin of error is the standard error, which we just found, times my z star. Now remember, this is our critical z-score. We talked about that a couple of pages ago. Your z star really depends on the confidence level over here. And you can consult your critical z-score table. There should be one right above this video. But the z-star corresponding to a 95% confidence interval would be 1.96. So my z-star is 1.96. If you want to take a moment to write all of this information down at the beginning of the problem, I tend to think that that's a very good idea. So I'm going to go ahead and find my margin of error next. Standard error is 0.0119 times my z star is 1.96. So I'm going to go ahead and multiply that out. 0.0119 times 1.96 gives me 0.0233. Again, I'm going to round to 4 decimal places because we're working with such small decimals. So there is my margin of error, which is a really important number. The last thing that I need to do at this point is to actually go and build my confidence interval. So I want to, for my confidence interval, take p hat plus or minus my margin of error. So p hat being my point estimate. Remember that this is a piece of information about my sample. And then the margin of error is attempting to account for some of that sampling bias that we talked about earlier on in this chapter. So p hat, we said that was 0.82. So 0.82 plus or minus my margin of error, which is 0.0233. Now, this looks like one calculation, but it's really actually 2. I have 0.82 minus 0.0233, and then I also have 0.82 plus 0.0233. I would recommend taking a second to write out both of these because we are going to have to calculate both of these. When we write out our confidence interval, we always want the smaller number first, and that is something that matters. That is something that I'm going to be picky about, which means that the minus case right here always goes first. So grabbing my calculator, 0.82 minus 0.0233, I ended up with, for my lower bound, 7967. And then for my upper bound, I'm going to do now the the positive case, the plus case. So I want 0.82 plus 0.0233, and that will give me 0.8433. Now, when we write our confidence intervals, most often we'll be writing those in interval notation. So that's going to look like blank, comma, blank in parentheses. And it's saying, here's your lower bound, kind of the left bound of that interval, and here's the upper bound. So in this case, I would say 0.7967, comma, 0.8433 is how I would write that confidence interval. And what that represents, remember, is that if I was to draw this out, here's my p hat of 0.82. The lower bound over here is 0.7967, and the upper bound is 0.8433. And what I'm trying to say with this confidence interval is that this range of values, everything that lives between these two numbers, is a feasible value or a feasible guess for our population proportion P. So it's going to be really important that we write this in this interval notation. That's how I would like to see your